Hey guys, I'm going to start tackling some past FRQs. First one I'm going to start with is 2016 question number 1, which is primarily an enthalpy question, but it's got electronic structure, it's got intermolecular forces, it's got a lot of good information. So part A of this question, students going to investigate the enthalpy of solution for two alkali metal halides with the same anion. They have access to a calorimeter, a balance, and thermometer. So part A says to measure the enthalpy of solution for lithium chloride, the student's going to add 100 grams of water, initially at 15 degrees Celsius to a calorimeter. They're going to add 10 grams of lithium chloride, stirring to dissolve. And after the lithium chloride dissolves completely, maximum temperature reaches 35.6 degrees. So you should recognize that this is, a Q problem. They've given you there's your CP, they've given your final temperature and your initial temperature. Where students get confused is on the mass. Be careful. They're asking you the magnitude of the heat absorbed by the solution. Your solution is both your solute and your solvent. So the mass of both of those need to be included in your Q problem. So when we do this, we're going to take the mass of the water, which is 100 grams. And you're going to add the mass of the lithium chloride. Your CP, because it's mostly water, is going to be the specific heat for water. Be careful too, that is joules. But I notice right away that the next question is asking for kilojoules, so I'm going to convert it at the end. Get in the habit of converting it to kilojoules anyways. Joules is a very small unit in terms of heat, so we usually talk in terms of kilojoules. And your delta T is going to be 35.6, minus 15 degrees Celsius. And when you do that, your Q in terms of joules should be 9,470, which gives you 9.47 kilojoules. And I've got 3 significant figures because that's 3 significant figures. Our temperatures are all 3 significant figures. So that's part A. Big takeaway, massive solution has both of them. Part 2, they want to know delta H, so the enthalpy of the solution in kilojoules per mole. If you don't know where to even begin with this, start with your units of measurement. If it's for lithium chloride, you can figure out how many moles reacted, I don't like the term reacted, or how many moles dissolved because you've got grams. And you know the heat, the magnitude of the heat absorbed by the solution because you figured that out in 1. Usually they build on one another. So that's my kilojoules. I already figured that out. To figure out the moles of the reaction, I'm going to take 10 grams of lithium chloride. I'm going to divide that by my molar mass, which is 42.39 grams. 1 mole of lithium chloride, and I get 0.236 moles. So to figure out the delta H of solution, I'm going to take my kilojoules, which is 9.47, and I'm going to divide it by my moles dissolved, and I should get 40.1 kilojoules per mole. Okay, we can't stop here. When you are talking delta H, the sign matters, okay? So let's take a look at what's happening. My temperature is going, my solution, the temperature is going up. So when I dissolve this lithium chloride, it is going to be an exothermic reaction. If it's exothermic, that must be a negative value. All right. If you do not have the right value, the sign, they are going to take points off. So we have tackled A so far. We're going to move on to the next part of this problem. And this is where it gets into kind of why this is happening, or comparing lithium chloride to sodium chloride. So to explain the difference in enthalpy of solution for NaCl, the student's going to investigate factors that affect it. And they look at the ionic radius. And if you look at the ionic radius, my radius for sodium is larger than my radius for lithium chloride. And this is in your first period, this is in your second period. So the student consults references and collects the data. First part of I'm showing you all the different parts of this question because I do think it makes sense to read through all parts to see where they're going with it, because you can kind of get some clues. But they want to start with the electron configuration for the sodium ion. And then they want to know the principles, explain why that cation is larger than the lithium cation. Using this information, they want to know which one has a greater lattice enthalpy, and then they want you to label this. So we're going to tackle each part separately. So we're going to do B first. Okay. For this, be careful, you're talking about an ion. So if I were to just do sodium alone, sodium alone would be 1s2, 2s2, 2p6, and then, 3s1, okay, because it's a group 1. But since it's an ion, that goes away, because that's the electron. That is my valence electron. That's what I lost. So this would be the electron configuration for the sodium ion in the ground state. Okay. So if we go back to, if we want to explain why the sodium ion is larger than the lithium ion, we're going to go back to what we know about electron configuration. So our sodium ion, the electron configuration is 1s2, 2s2, 2p6, because it lost that 3s. Remember, it lost that 3s1. It got rid of that. Our lithium ion is just going to be 1s2. It should be 2s1, but it lost that. Okay, so you'll notice that we've got an entire new energy level for sodium. So the sodium ion is going to have 2 electrons on that first energy level and 8 electrons on that second, whereas lithium only has the 2 electrons. So this is obviously bigger than that one, and that explains why the sodium ion is bigger than what we know about electron configuration. Whoops. All right, this one should be very straightforward. This one, I hope that none of you get it wrong. They're showing a lattice structure of a lithium chloride salt, and they want you to identify the ions. So lithium and chlorine, here's your positive ion. It lost electrons, so it lost its size. Chlorine ions gained electrons, so they are bigger. So your smaller ions should be your lithium ions, and your larger ions should be your chlorine ions. That is pretty straightforward. I hope none of you get that one wrong. The last part of this one, I think this is the last part of this question. They're talking about the lattice energy, and this gets into the IMFs. So there's a couple things happening here. Let's read through the problem. Lattice energy for lithium chloride is positive. So lattice energy, lattice enthalpy, sorry, indicating that it takes energy to break the ions apart. So it takes energy to disassociate lithium and chloride. However, when I dissolve the ions in solution, it's an exothermic process. So they want to identify all the particle-particle interactions that contribute significantly to the dissolution process being exothermic. So the first thing that they want you to do, and they want you to include the particles that interact. So before I start, I've got these salts with my lithium and chlorine, and I'm just going to draw two. So I've got my lithium ion and my chlorine ion. I've got, so those are ionic attractions between those two ions. And then I've got my water molecules. So I've got my water molecules. And my water molecules, there's an attraction between the water molecules. Sorry. So I've got that hydrogen bonding attraction between my water molecules. So I've got, here's my solid salt, and here's my water situation. Before I dissolve something, so before I separate these ions and surround them by my water molecules, I got to overcome the lattice energy here, and I got to overcome the hydrogen bonding here. So I have to use energy to overcome those attractions. And I'm so sorry. But I'm going to have to use energy to overcome those attractions. And after I'm done, when that's done, I'm going to have my lithium ions, which are positive, and there's going to be some attraction between the negative end of my polar molecule, and then my chlorine ions are going to be attracted to the positive end of my polar molecule. And when this happens, this is going to release energy. Okay, so I've got two different things happening. So what they want you to do is, for each interaction, include the particles that interact and the specific type of intermolecular force between those particles. Well, I've got my lithium particle reacting with the negative end of my polar water molecule, and I've got my chlorine ion interacting with the positive end of my polar molecule. So those attractions are called ion-dipole interactions. Okay? I'm overcoming the lattice energy and the hydrogen bonding and creating these ion-dipole interactions. And so since it is exothermic, there must be more energy released from this ion-dipole interaction than the energy used to overcome the lattice energy and the breaking of the hydrogen bond information. So that is problem number one. In the next video, we'll tackle problem number 2.